Welcome back to the 2021 GCSE paper, Higher Single Award, and we're now on 6.3. We're continuing on where we left off, where the student wants to compare the reactivity of a known metal Q with zinc. Well, then they've given you this equipment. To do this, it's just quite simply like hopefully you've done in the past before, which is describe a method. And when they say describe a method, it means you have to literally describe it. What are you going to do? And I'm going to describe it, and I'll let you write down most of it, which is, of course, going to be 1. You're going to want to add both zinc and Q, but you're going to add them to different beakers. And each beaker, you're going to have your silver nitrate solution. Now, there's a couple things you need to remember, that you have to keep the mass the same for each if you're going to make this a fair test. So the mass has to be equal, and you're going to measure that in grams. It doesn't matter what mass you say. You could say 5 grams, you could say 1 gram, or you could just say that you're going to make sure that you measure the mass so it's equal. For the silver nitrate in the beaker, you're going to have to say that the volume is the same, and that is going to have to be in centimeters cubed. And you're going to have to make sure that you either say a number like 25 or 10 or 15, or just say it's going to be equal. Now that you've said that you're going to add it to separate ones, you're going to add in a thermometer beforehand, and you're going to get an initial temperature, and then you're going to wait for a given period of time, and let's say it's 5 minutes, 2 minutes, or you could say till the maximum temperature has been reached. Whatever it is, you need to be very explicit. Then you're going to take the max or min, you're going to minus from the initial, and you're going to get a change in temperature. Once you've got that, you're going to compare them, zinc and Q, the temperature change, and you're going to say that the one that has the highest temperature change, or the most temperature change, is going to be most reactive. So it's worth 4 marks, and you need to make sure that you put in the variables you're keeping constant, a step-by-step and a comparison at the end, as well as what you actually are going to say is after the comparison about which one is the most reactive. Moving on. This question is about chemical reactions in electricity. Electrolysis and electrical cells both involve chemical reactions in electricity. Explain the difference between the process of electrolysis and in a chemical cell. Now, for you didn't have to do this one. So I'm going to skip it, because this is the only thing that we hadn't covered. Next, a teacher demonstrates the electrolysis of molten lead bromide. Bromide is produced at the positive electrode. Complete the half equation. Well, bromine is a group 7, which means it's going to be diatomic, so you need 2 of them. And of course, you're going to lose an electron. Now, if you have 2 bromine, you need 2 ions to make the bromine atoms. If you've got 2 bromine ions, you have to lose 2 electrons. So overall, you need to have 1, what your products are, and you have to balance it. This one's a bit more complicated. 2 aqueous salt solutions are electrolyzed using inert electrodes. Complete the table. Well, they want to know the positive and the negative electrode. So I'm going to be a bit cheeky here, and I'm just going to make a positive and a negative electrode above. I know that's copper nitrate, and that's positive for the copper. The nitrate is negative. Potassium is positive because it's a metal, and iodine is negative. But because they use the word aqueous, I know also that there's going to be an OH ion, and there's going to be a hydrogen ion, both from the water. And they've said both of these are aqueous. Now, between the two positive ions, they're both going to try to go to the negative. Well, they both will go to the negative, but when they get there, the least reactive will be removed. So at the negative ion, that's going to be copper. At the positive electrode, the two negative ions will go. And as they get there, the least reactive will be removed. Now, this is going to be hydroxide, but the only problem with hydroxide is it will actually be removed as oxygen gas. I'll actually write the word oxygen instead. Next, at this one, we're going to do the same thing. Between hydrogen and potassium, we know that potassium is very reactive, so hydrogen will come out, so I'll write it out. And in this case, between the iodide and the hydroxide, we know that the halogen will come out, so that's going to be iodine. So oxygen, iodine, and hydrogen. Remember, they say aqueous, you have to add in your hydrogen and your hydroxide ions into the mix. Some students investigated the electrolysis of copper nitrate using inert electrodes. The student investigated how the mass of copper produced at the negative electrode varied with time and current. And that's quite a long list of what they did. So, I'm not going to do that. I'm just going to jump ahead. Some of the copper produced did not stick to the negative electrode, but fell to the bottom of the beaker. Suggest how the student could find the total mass. Well, I'm going to look at my diagram, and I'm going to say that there's some copper stuck here, and I'm going to say that there's some copper at the bottom. Oops, my mistake. I got to erase that pretty quickly before anyone notices. That copper is going to go to the negative electrode, and I'm going to have some copper at the bottom. So they're saying that how am I going to find the total copper if I weigh this and some has dropped off? Well, that's not too hard. First of all, I'm going to have to weigh initially the electrode. Then I'm going to have to weigh it after. And I'm going to take the after minus the initial, and that's going to give me the mass of the copper on the electrode. But that's not going to give me the mass of the copper in the bottom. To do this, I'm going to have to do the long, very boring thing, which is pour it through a filter paper, and then I am going to have my copper there. But I'm going to have to rinse it as well to remove any of the copper nitrate solution. And then after that, I'm going to have to take my copper and I'm going to dry it in an oven. Before I say anything else, I should probably also say, after I weigh it, before I weigh it, I will also need to dry it completely. And that way there's no copper nitrate solution left on that will also interfere with my mass. So, once I have my dry copper from my filtering process, and I have my difference on my electrode, I'm just going to add them together. So I'm going to add up this copper, we'll call that A, and I'll add up this copper, which we'll call B, and you'll get my total copper mass. Student then plotted their results. The student correctly concluded that the total mass of copper produced is directly proportional to the time and to the current. How do the results in figure 5 support the conclusion? Well, that it is mass is proportional to time. I'm going to circle mass and time. And for each of these lines, they are linear, which means they're a line. A linear proportion, which means that the increments let me see if I can get a bit more space. There we go. increments for mass and time are proportional. Now the only problem is here it says directly proportional. So I'm not sure I could use the proportional even if I use the word increments for mass and time. So I'm going to say it's a linear line. Next, how do the results in figure 5 support the conclusion that the total mass is directly proportional, again, to current? Well, if I'd like to look at my, or their very, very nice table. The difference between 0 and 0.3 is 0.3. The difference between 0.3 and 0.6 is 0.3. The difference between 0.6 and 0.9 is 0.3. Then, if I go over here, I can see that the difference between, on this case, for the mass produced, depending on the current, is going to be 1.8. And then again, the difference is 1.8. And again, the difference is 1.8. So I could just say the increments of the change in current is directly proportional or to the change in mass, and I'm going to actually give the numbers as current changes. By 0.3 amps, the mass changes by 1.8 grams. There we go. Copper nitrate solution is blue. Suggests why the blue color fades. Well, copper ions become copper metal. You could also say that the copper nitrate solution gets less concentrated. And that makes sense as the ions move away because they are now becoming a solid, and it's copper, because it's a transition metal, that gives the copper nitrate solution its beautiful blue color. And so as you remove the ions, it turns less blue. Determine the number of atoms produced, or number of atoms of copper produced when copper nitrate solution is electrolyzed for 20 minutes at a current of 6 amps. Well, if you forgot that this is question 7 and they can ask you questions from earlier in question 7, you're going to find it rather difficult. I'm going to erase this a little bit to get rid of some of my scrawl. And go again to, it's asking, let's see, using the graph, 0.6 and 20 minutes. So let's go to 0.6 and find 20 minutes and go up. And that is going to be 0.22, 0.24. And I like to use a ruler, but I'm not going to have one here because if I did use it on my screen, you wouldn't see it. And that's 0.24. So I now know I have 0.24 grams at this time. But they want to know the number of atoms. To do this, I have to convert it to moles first. So I'm going to remember my equation is mass divided by mR is equal to moles. I know that 1 mole is equal to 6.02 times 10 to the 23rd things. So I'm going to say atoms, in this case of copper. So I just need to work out moles first. So that's 0.24 and copper is 63.5, which they've just given me from over there. And that will give me my total number of moles. Let me get out my calculator. Oh, there we go. That's not a lot of moles. So I then next need to multiply that by Avogadro's constant, or Avogadro's number. And that will give me, and how many figures? 3. I don't want to write down too many, so I'll just go for the 3, which is going to be 2.28 times 10 to the 21st. This question is about the reaction between hydrogen sulfide and oxygen. I can't help it, I've got to look at my molar ratios. What does H2 represent? Well, the reason why it's got a G there, because we need to say that it is steam. We could say that it is water as a gas. Calculate the volume of oxygen required to react 50 centimeters cubed of hydrogen sulfide. Now I know why they decided to make that a gas, because I know that any mole, 1 mole of any gas equals 24 dm cubed. So if I have 1 mole of this, I'll make 1 mole of that. If I had 1 mole of that and 1 mole of that, that means I'd have 24 of this and 24 of that. But the ratio is different. It's 2 to 3. So if the ratio was 1 to 1 earlier and they gave me 50, that would mean 50 to 50. But that's not what the case is here. In this case, the ratio is going to be 2 to 3. So 50 centimeters cubed. And the ratio of the gas is going to be 2 to 3. And that's going to give me 75 centimeters cubed. This reaction is exothermic. As soon as they say exothermic, I'm not going to read much more. I'm just going to put my line down and go across. Exothermic means energy has to exit. Next, complete the energy profile line. Well, that's done. Label the activation energy. I'm going to make a dashed line here, always from the reactants, and I'm going to make a single arrow up from that line. And I'm going to label it EA for activation energy. Then I'm going to go across from my products line. I'm going to put down P for products. And I'm going to go over here. And the difference between the reactants and the products is going to be my change in energy. But because it's exothermic, it's going to be negative delta H. An accounting question. Because that's really what this is. Numbers in and numbers out. This figure 7 shows the displayed formula for the reaction of hydrogen sulfide again and oxygen. This shows the bond energies. Now you'll notice that this one is missing. In the reaction, the energy released from forming new bonds is 1034 greater than needed to break them. Now this means that more energy is going to go out, which means that this is going to be negative. It's saying that this is an exothermic reaction. So if I were to do it this way, I could say that the reactants, to break them, is always going to be positive energy in. The products, to make them, is always negative energy out. And that's going to be equal to a negative 1034. Now, I'm just going to start plugging in some numbers for all of these. So, first off, is I have 1, 2 times 2. So there's going to be 4 of these hydrogen sulfide bonds, which is going to be 4 times 3, 6, 4. And then I'm going to add in 3 of these oxygen bonds. And that is going to be 3, because there's 3 of them, times a 4, 9, 8. Then I'm going to have on this side hydrogen-oxygen bonds, and I have 1, 2 times 2, which is going to be 4, times 4, 6, 4. And then on this side, I'm going to have, well, I have no idea what that is, but I know I'm going to have 4 of them, so I'm going to call it 4x. Now I just need to simplify. If I solve for x, that just means x is going to be equal to 5, 3, 2. And that's your answer. This question is about acids. Hydrogen chloride and ethanoic acid both dissolve in water. All hydrogen chloride molecules ionize in water. Approximately 1% of ethanoic acid molecules ionize water. Well, this tells me that this is hydrogen chloride is going to make a very strong acid. It's also going to tell me that ethanoic acid is going to make a weak acid. So I now need to say that if I have 1 gram of hydrogen chloride and it completely ionizes, this means I'm going to have hydrogen chloride is going to ionize into hydrogen ions and chlorine ions. Now, I need to figure out how many moles there are. If I have 1 gram of this, I'm going to have probably, well, let's see, how many grams of hydrogen? Well, 1 as an atom economy. You know what? I'm not even going to work this out. I do know that it's going to be quite strong, because for every mole of hydrogen chloride, I'm going to have 1 mole of HCl. So if I figure out the number of moles of HCl, let's see, 1 plus 35.5 is equal to 36.5, and I have the mass of 1 divided by 36.5. Well, that's actually going to be quite strong. Let me get my calculator. That's going to be 0.027 moles. All right, that means if that's how many moles of HCl I've got, that's also how many moles of hydrogen ions I'm going to have. All right, so I now know that I now have that many moles, but I also know that the pH is equal to the negative log of the hydrogen ion concentration. And the negative log of that is going to be 2. So I can say that the pH is going to be around 2, about 2, and well, around 2. And it's a strong acid. So a constant, which is the correct description of the solution, a concentrated solution of a strong acid, a concentration of, no, it's definitely not weak. It's definitely not weak. So is it dilute or is it strong? Well, I'd say it's pretty strong. Which solution? Oh, I believe this is the right answer for this one. I will be checking with the mark team later. Which solution would have the lowest pH? Well, that's easy. The one with the lowest pH has got to be the most acidic, which means it has to have the highest concentration of acid, which is not going to be this one or this one, and it has to be the strong acid, which is going to be that one, which of course is the hydrogen chloride from before. Student investigate the concentration of sodium hydroxide by titration with ethanoic acid solution. So first of all, this is their method, and they want to know 2 improvements. Well, as a general rule, if they don't include a white tile, you should say there's a white tile that's required to see when the indicator changes. Also, you're going to have at least 3 titers within 0.1 centimeters cubed of each other and do an average. Also, you might want to, near the end, after doing a rough, go drop by drop, but only when you reach near where the rough was. So first do a rough, then you do your later ones, going drop by drop near where you think it's going to be. You can't just do drop by drop, you'll be there all day. And also you're going to need to swirl that as the indicator changes to make sure that you haven't gone under or over. Other things that you may be able to do are avoid parallax by looking perpendicular to your burette. And I think those are the main ones. Next, ethanoic acid is a solid at room temperature. Calculate the mass of ethanoic acid. Need to make that volume of a solution at that concentration. Well, this looks like another ratio problem. I know that 250 centimeters cubed in relation to 1,000 centimeters cubed, which is a decimeter cubed, is a ratio of 1 to 4. So I now need to work out using my concentration equation. Concentration is equal to moles divided by volume. So C times V is equal to M. I have my concentration. Now, I know in this case that I've got moles, and that is here in moles. But they want grams, they want mass. So I could just leave this as it is and use my other equation, which is going to be mass divided by AR is equal to moles. And I would like to actually calculate the number or the mass. So I'm going to take mass is equal to moles times the AR. All right, so if I do this, and instead of having moles per volume, I'm going to have grams per volume if I can convert the moles to grams and just leave it as it is. So I'm going to take the moles and the AR, the moles times the AR, which is 90, and I'll end up with 4.32 grams. But I can't forget that I don't need all of that. I only want to make 250. The ratio is 1 to 4, divided by 4, and I'll get 1.08. Next, the student found that 25 centimeters cubed of sodium hydroxide was neutralized by 15 centimeters cubed of that concentration. Okay. I'm sorry, I'm going to do this the long, boring way. I'm going to start off with making my table. Acid, alkali, and on this side, I'm going to have concentration. I'm going to put down my moles. I'm going to put down my volume. And I'm going to put down my ratio. And now I'm just going to start filling in some numbers. Well, first of all, I'm going to come over here and say the student found sodium hydroxide of 25. So volume 25. Then was neutralized by 15 of the acid. Come over here to the volume of the acid, 15. For this concentration of the acid, so I can put that over here, which is going to be 0.448. So I'm looking for concentration of the alkali. To do this, in the last part, sorry, how could I have forgotten my ratio? The ratio is 1 to 2. So for every 2 alkali, I have 1 acid. So I'm going to put a 2 there and a 1 there. For every 1 acid, I have 2 alkali. So I now need to figure out the number of moles. So I'm going to go back to my formula and I'm going to put down concentration is equal to moles divided by volume. If I'm looking for moles, then moles is going to be equal to concentration times volume. So it's going to be concentration times volume, and that will give me 0.72. Now I need to move across to here. I'm going to use my ratio from moles to moles. 0.72, I now need to double it because my ratio is 1 to 2. 1.44 for my moles. Now I need to work out my concentration, my final one, and that concentration is moles divided by volume. I have moles, I have volume, and I'll move that over there. When I do this, I'm going to end up with 0.0576, and I'll put it over here. 0.057. I like to keep it to maybe 2 or 3 significant figures, but in this case I'm going to do 2. And the reason why is I'm going to take a look at my data. They have 2. This does go to that, but no, I'm going to stick with the 2. 0.057. Oh, hope that was okay. That was very fast, and thank you.